The most mysterious star in the universe, known to astronomers and space enthusiasts alike as the Pinwheel Star, WR-104, is a celestial object that has captivated imaginations, sparked scientific debates, and even instilled fear for a time. Its enigmatic nature lies not just in its dazzling beauty, but in the cosmic danger it once seemed to pose. WR-104 sits approximately 8,000 light-years away in the constellation Sagittarius, a relatively close distance on the astronomical scale. Yet, what makes it genuinely fascinating and terrifying is not just its proximity, but the possibility that its eventual demise could produce a gamma-ray burst, a beam of energy so powerful it could potentially disrupt life on Earth if pointed directly at us. The Pinwheel Star has been described as a cosmic dancer, spinning in a graceful, spiraling waltz with its stellar companion. Its rotating pattern of dust and gas forms an almost hypnotic spiral, visible in infrared observations, earning it the nickname Pinwheel Star. This star is not just a single entity, it is part of a binary system, and its behavior is deeply intertwined with the gravitational and energetic interactions with its partner star. The first time scientists observed the spiral pattern, they realized that WR-104 wasn't merely a static point of light. The Pinwheel Star is a living laboratory of extreme astrophysics, demonstrating phenomena that we cannot replicate on Earth. The very matter composing the star, the violent winds, and the powerful radiation it emits are all forces that shape its surroundings in profound ways. Early models suggested that this star might one day be capable of generating a gamma-ray burst, an intense flash of energy that could strip away Earth's ozone layer and trigger catastrophic environmental changes. The sheer thought of a star relatively close in cosmic terms having the potential to harm our planet captured headlines and drove a flurry of research. Scientists and enthusiasts alike were drawn to it, fascinated by both its aesthetic beauty and the existential questions it posed. The story of WR-104 starts with its classification as a Wolf-Rayet star, a class of stars that are inherently fascinating and dangerously unstable. The Pinwheel Star, as a Wolf-Rayet star, represents the pinnacle of stellar extremity. What truly defines it, and its Wolf-Rayet siblings, is a combination of mass, luminosity, and violent behavior. These stars are incredibly massive, often 20 to 60 times the mass of our Sun, and their immense gravity drives nuclear fusion at such an accelerated rate that their lifespans are incredibly short on cosmic scales, typically only a few 100,000 to a couple of million years. This makes the Pinwheel Star a blazing beacon of both brilliance and instability. Unlike ordinary stars that live stable, long lives, Wolf-Rayet stars burn through their fuel quickly, creating conditions ripe for dramatic endings. One of the most striking features of these stars is their prodigious stellar winds. The Pinwheel Star emits winds moving at thousands of kilometers per second, stripping away its outer layers and revealing the hot, dense core beneath. This process not only shapes the star itself, but also profoundly influences its surroundings. The material expelled in these winds enriches the surrounding interstellar medium with heavy elements, which later contribute to the formation of new stars, planets, and even the building blocks of life. In essence, the Pinwheel Star is both a destroyer and a creator, a paradox that has fascinated astronomers for decades. The intense radiation and extreme temperatures of Wolf-Rayet stars, like the Pinwheel Star, make them some of the most luminous objects in the galaxy. They shine hundreds of thousands, sometimes millions, of times brighter than the Sun, yet they are not often visible to the naked eye because they are relatively rare and frequently obscured by cosmic dust. This rarity adds to their allure, as astronomers know that observing one offers a glimpse into the future of massive stellar evolution, including the processes that might lead to spectacular supernovae or even gamma-ray bursts. It is precisely the combination of immense energy, instability, and potential for catastrophic events that makes Wolf-Rayet stars dangerous. The Pinwheel Star, with its highly evolved state, is essentially a ticking cosmic time bomb. If conditions align just right, its inevitable death could produce a gamma-ray burst, an intense beam of high-energy radiation capable of wreaking havoc on nearby planetary systems. This duality, immense beauty and existential threat, is what elevates the Pinwheel Star from being just another luminous point in the sky to one of the most mysterious and compelling objects in astrophysics. Now we turn to the star that has captured the imagination of astronomers and space enthusiasts alike, the Pinwheel Star itself. What makes it so mesmerizing isn't just its intrinsic brightness or its classification as a Wolf-Rayet star, but the spectacular visual phenomenon it creates. A cosmic pinwheel of spiraling dust and gas that seems almost artistically designed. This pattern is not merely a trick of light, it is a direct result of the star's binary nature, a celestial dance between two massive stars locked in an intricate gravitational embrace. The Pinwheel Star is not alone. It shares its system with a massive OB-type companion, a hot and luminous star in its own right. The interaction between these two stellar titans is what gives rise to the spiraling structures we observe. As the Wolf-Rayet star emits its powerful stellar winds, the winds collide with those of its companion, creating shock fronts that compress and heat the gas and dust in a unique pattern. These interactions are not static. They rotate along with the orbital motion of the binary stars, resulting in the continuous formation of the iconic spiral that astronomers can observe in infrared light. Infrared observations reveal the full splendor of this cosmic artwork. Visible light alone cannot penetrate the dense layers of dust, but infrared wavelengths allow us to see the intricate spiral winding outward from the stellar pair. Each turn of the spiral represents material expelled during one orbit of the binary stars, effectively acting as a timestamp that records the violent and dynamic history of the system. The result is a stunning, almost hypnotic visual, a literal cosmic pinwheel stretching across astronomical distances. But the Pinwheel Star is more than just a beautiful display. This binary interaction is a natural laboratory for studying stellar evolution and extreme physics. By observing the spiral, astronomers can measure wind speeds, determine the masses of both stars, and even infer properties of the dust being created. The patterns themselves reveal subtle clues about the orientation of the system, the intensity of the winds, and the dynamics of material being ejected into space. It's a rare opportunity to witness, in real time, the dramatic life cycle of massive stars on the verge of their ultimate fate. What makes the Pinwheel Star so enigmatic is how this beauty is tied to potential danger. That same spiraling material, generated by the violent interplay of stellar winds, hints at the immense energy contained within the system and the extraordinary events it could unleash in the future. Yet, despite the risks, there is something undeniably captivating about observing this cosmic choreography, an awe-inspiring reminder that the universe can be both beautiful and deadly at the same time. The Pinwheel Star's mesmerizing spiral is only the surface of a far more intricate cosmic story. A story written in the delicate balance of gravitational forces, stellar evolution, and the raw power of stellar winds. Central to this story is the binary nature of the system. The Pinwheel Star is not a solitary luminary. It shares its existence with a massive OB-type companion star. This partnership is what allows the Pinwheel Star to create the spiraling dust patterns that have earned it both scientific attention and popular fascination. The binary system is locked in an orbital embrace that lasts approximately 8 months, a relatively short period on cosmic timescales. Despite the brevity of a single orbit, the implications of this dance are vast, both visually and scientifically. The binary dance begins with the gravitational relationship between the Pinwheel Star and its OB companion. Both stars exert tremendous gravitational forces on each other, forcing them into a close orbit where each completes a revolution around a shared center of mass every 8 months. This orbital period is particularly intriguing because it sets the rhythm for the formation of the pinwheel spiral. Each rotation corresponds to a new layer in the spiral, effectively allowing astronomers to read the history of the star system by studying the spacing and structure of the spiral arms. In essence, the Pinwheel Star serves as a cosmic metronome, marking the passage of time in a universe where human scales of hours, days, and years are inconceivably tiny. The OB companion star plays a crucial role in shaping the dynamics of the system. OB stars are among the hottest and most massive stars known, often exceeding 15 to 20 times the mass of the Sun and radiating immense quantities of ultraviolet light. Its gravitational influence stabilizes the orbit, preventing the Pinwheel Star from ejecting its material chaotically into space. More importantly, the OB companion's own stellar wind collides with that of the Pinwheel Star, creating a turbulent interface where matter is compressed and heated. These collisions generate shock fronts that provide the physical basis for the formation of dust grains, which then spiral outward in an organized pattern, tracing the motion of the binary orbit. Without the OB companion, the Pinwheel Star's wind would expand more randomly, and the iconic spiral pattern would never form. The two stars are locked not only by gravity, but by a shared history of stellar interaction, making them inseparable architects of the system's spectacular appearance. The geometry of the orbit adds another layer of complexity to the binary dance. Observations suggest that the orbit is not perfectly edge-on as seen from Earth, but slightly inclined, creating subtle asymmetries in the spiral structure. This inclination affects how astronomers interpret the orientation of the system, which was once thought to pose a direct gamma-ray burst threat to Earth. By analyzing the spiral's shape and velocity, researchers were able to infer the tilt of the orbital plane, leading to the recent conclusion that the Pinwheel Star's orientation reduces the risk of a catastrophic event. The orbital inclination also influences the density and temperature distribution of the dust, which in turn affects the infrared emission that makes the spiral observable. This complex interplay of orbital dynamics, stellar winds, and dust formation highlights just how intricate and finely tuned these massive binary systems are. The energy dynamics in the binary system are staggering. Both the Pinwheel Star and its OB companion are pumping out material and radiation at extraordinary rates. The Wolf-Rayet star alone loses mass at a rate of about 1/1,000,000th of a solar mass per year through its wind, which might seem negligible but accumulates over the star's remaining lifespan to a mass equivalent to several suns. The OB companion, while not as extreme in mass loss, contributes its own fast-moving wind, and where these winds collide, temperatures can reach millions of degrees, producing X-ray emissions detectable by space telescopes. These high-energy collisions are not just a spectacular light show. They provide key insights into the physics of high-energy astrophysical processes. By studying the interactions between the two stars, astronomers can learn how massive binaries influence galactic ecology, contribute to the enrichment of the interstellar medium, and even set the stage for the final explosive deaths of massive stars. One of the most compelling aspects of the binary dance is how it acts as a natural laboratory for extreme astrophysics. The Pinwheel Star and its companion provide a unique window into the late evolutionary stages of massive stars, a phase that is both brief and violent compared to the billions of years most stars spend on the main sequence. These systems allow scientists to test theoretical models of stellar evolution, particularly how massive stars lose mass and transfer angular momentum. In turn, these models are crucial for understanding phenomena such as supernovae and gamma-ray bursts, which can have far-reaching consequences for their galactic neighborhoods. The Pinwheel Star, by virtue of being relatively close and exhibiting such a clear and structured spiral, offers one of the best observational cases for studying these processes in detail. The orbital dynamics of the binary system also provide clues about the eventual fate of the Pinwheel Star. The close proximity and gravitational interaction with the OB companion can influence the rotation rate of the Wolf-Rayet star, potentially affecting the alignment of its rotational axis. This alignment is critical when considering the likelihood of a gamma-ray burst. Rapidly rotating Wolf-Rayet stars with rotational axes aligned toward Earth could, in theory, produce directed bursts of energy with catastrophic consequences. Fortunately, as current observations indicate, the binary dance of the Pinwheel Star appears to tilt its axis away from direct alignment with our planet, significantly mitigating the potential threat. Nevertheless, the system remains an object of intense study because its ultimate death will still be one of the most energetic stellar events in our local galactic environment. Another layer of fascination comes from the orbital eccentricity and stability of the binary system. While the orbit is not perfectly circular, it is sufficiently stable to maintain the integrity of the spiral pattern over multiple cycles. Any significant perturbation could disrupt the formation of the pinwheel, scattering dust and gas in more chaotic trajectories. The delicate balance of gravitational forces, wind pressures, and orbital motion is a testament to the finely tuned dynamics of such massive binaries. This stability allows astronomers to use the observed spiral as a direct probe of the orbital mechanics and mass loss processes, making the Pinwheel Star not just visually stunning, but scientifically invaluable. The binary dance is also a window into cosmic timescales. Each orbit, each turn of the spiral, represents roughly 8 months of activity, but these spirals extend over thousands of astronomical units, capturing a record of the system's behavior over decades and centuries. By studying the structure of these spirals, astronomers can reconstruct the history of mass loss, measure wind velocities, and understand the rhythm of material ejection in extreme stellar environments. It is almost as if the Pinwheel Star keeps a diary in the language of dust and gas, documenting its tumultuous life for those patient enough to observe and decode it. The binary dance is what gives the Pinwheel Star its iconic nickname. Without the precise interaction between the Wolf-Rayet star and its OB companion, the star's dust emission would be chaotic, lacking the symmetry and hypnotic regularity that gives the impression of a spinning pinwheel in space. The combination of orbital mechanics, colliding winds, and dust formation is rare in the galaxy, making the Pinwheel Star a unique and compelling example of what can happen when two massive stars come together in a close, high-energy partnership. It is this combination of beauty, danger, and scientific richness that has made the Pinwheel Star one of the most studied, admired, and enigmatic stars in our cosmic neighborhood. The Pinwheel Star owes its name and much of its intrigue to a phenomenon now widely referred to as the pinwheel effect. This effect is the direct consequence of the violent interplay between the stellar winds of the Wolf-Rayet star and its OB companion. While the binary dance sets the stage, the pinwheel effect is the dazzling visual performance that brings the system to life, manifesting as a continuous, spiraling emission of dust and gas observable in infrared light. To understand why the pinwheel effect is so captivating, one must first delve into the physics behind colliding stellar winds, the dynamics of dust formation, and the unique orbital mechanics that convert these violent interactions into a hypnotic spiral. Both stars in the Pinwheel Star system emit intense stellar winds, but these winds differ in speed, composition, and density. The Wolf-Rayet star expels material at extraordinary velocities, often exceeding 2,000 kilometers per second, and carries a wind rich in heavier elements like carbon, nitrogen, and oxygen. These are the byproducts of nuclear fusion taking place in its core and outer layers, now exposed due to the star's extreme mass loss. In contrast, the OB companion emits a somewhat slower but still highly energetic wind composed primarily of lighter elements. When these two winds collide, they do not simply mix harmlessly. Instead, the interaction generates a shock front, a region of extremely high pressure and temperature where the gas is compressed and heated to millions of degrees. These shocks are the engines of the pinwheel effect. The high-energy collision between the two winds creates localized regions of turbulence that allow dust to condense. Under normal circumstances, dust cannot survive in the intense radiation fields near massive stars because the heat and ultraviolet radiation would destroy it almost instantly. However, in the colliding wind interface of the Pinwheel Star system, the compression of gas behind the shock front provides pockets of density and shielding that permit dust grains to form and persist. Once formed, these dust grains are carried outward by the stellar winds, tracing the orbital motion of the binary stars. This combination of orbital rotation and continuous material ejection produces the spiraling structure that is observed in infrared. Infrared light is key to observing the pinwheel effect because the dust itself absorbs visible and ultraviolet light and re-emits it at longer wavelengths. Ground-based infrared telescopes, as well as instruments like those aboard the Keck Observatory, have allowed astronomers to resolve the spiral in unprecedented detail. Each loop of the spiral corresponds to one orbit of the binary system, effectively creating a layered timeline of material ejection. This is why the pinwheel effect is not merely a static decoration, it is a living record of the system's dynamic interactions. By analyzing the brightness, spacing, and velocity of the spiral arms, researchers can infer properties of the stellar winds, such as their speed, density, and even chemical composition. Another fascinating aspect of the pinwheel effect is how it depends on the orbital geometry. Because the binary system is inclined at a certain angle relative to our line of sight, the spiral appears nearly face-on, creating the illusion of perfect symmetry. This near face-on orientation initially led scientists to speculate about the possibility that the Pinwheel Star's rotational axis might be aligned toward Earth, raising alarms about gamma-ray burst risks. Later observations clarified that the system is tilted away by about 30–40 degrees, which significantly reduces any potential danger. Nevertheless, the apparent perfection of the spiral remains a captivating optical illusion born from the combination of orbital mechanics and material physics. The pinwheel effect is not just beautiful, it provides a natural laboratory for understanding fundamental astrophysical processes. Colliding winds generate X-rays, which can be observed to study high-energy interactions in extreme environments. The dust, meanwhile, is a tracer of mass loss, allowing scientists to calculate how quickly the Wolf-Rayet star is shedding material and how this material enriches the surrounding interstellar medium. These insights are crucial for building accurate models of stellar evolution, particularly for massive stars that will end their lives in spectacular supernovae or potentially gamma-ray bursts. In this sense, the pinwheel effect links aesthetic fascination with profound scientific significance. It is both a cosmic artwork and a tool for unlocking the secrets of extreme astrophysics. The spiral itself can extend over vast distances. Each successive turn moves outward, carried by the continuous flow of stellar winds, and can eventually span several hundred astronomical units. Observations over time have confirmed that the spiral is persistent and stable, a testament to the precise balance of forces in the binary system. Despite the turbulence inherent in the collision of supersonic winds, the pinwheel effect demonstrates remarkable order. This stability allows astronomers to study the system over decades, tracking changes in wind speeds, orbital period variations, and the evolution of the dust's composition. In effect, the Pinwheel Star offers a real-time view of the life cycle of massive stellar binaries. In addition to its scientific value, the pinwheel effect has captured the imagination of the public. Images of the spiraling dust cloud have been featured in countless science articles, documentaries, and educational materials. The almost hypnotic symmetry of the spiral, combined with the knowledge that this system could eventually produce one of the most energetic events in the galaxy, creates a dual sense of awe and respect for the forces shaping the universe. The Pinwheel Star demonstrates how the cosmos can simultaneously be beautiful, violent, and deeply informative, a celestial paradox that embodies both creation and destruction. The Pinwheel Star's breathtaking visuals and violent stellar dynamics are all the more striking when we consider its cosmic proximity. At approximately 8,000 light-years from Earth, it resides relatively close on the galactic scale, in the direction of the Sagittarius constellation. To most people, 8,000 light-years might sound unimaginably far, and in human terms, it is certainly beyond comprehension. But in astronomical terms, especially when discussing events as catastrophic as gamma-ray bursts or supernovae, this distance is close enough to matter. It is close enough for its fate to have potential implications for our planet, and close enough for astronomers to study its intricate details with modern observational instruments. To put this into perspective, the Milky Way galaxy is about 100,000 light-years in diameter, making the Pinwheel Star relatively nearby in our own galactic neighborhood. Most stars in the galaxy are scattered far beyond this distance, meaning the Pinwheel Star is within a few percent of the galaxy's breadth from us. This proximity provides a unique advantage for astronomers. It allows them to resolve fine structural details in the pinwheel spiral, measure stellar wind velocities, and even study the chemical composition of the dust forming around the star. Observing a Wolf-Rayet binary at this distance is rare. Most massive stars of this type are either too far or obscured by interstellar dust. The Pinwheel Star's relative closeness is one of the reasons it has become such a focal point for both scientific research and public fascination. However, proximity also introduces a degree of concern. Wolf-Rayet stars are inherently unstable and destined to die violently, often in supernova explosions that can release massive amounts of energy. When a star like the Pinwheel Star is this close, its eventual death is not just an abstract event in a faraway galaxy. It is a potential cosmic event that could, in theory, affect our own solar system. For most supernovae, the dangers are limited to relatively nearby stars, usually within a few tens of light-years, where the shockwave and radiation could directly harm planets. But the Pinwheel Star adds another layer of concern: the possibility of a gamma-ray burst. GRBs are highly focused beams of radiation that, unlike a spherical supernova, can travel thousands of light-years without significant weakening. The fact that the Pinwheel Star is only 8,000 light-years away means that if a GRB were directed toward Earth, it could have serious effects on the biosphere, including damaging the ozone layer and triggering mass extinction events. This distance also means that observations of the Pinwheel Star allow astronomers to study processes in extreme detail without the confusion of intervening stellar material from other stars in denser regions of the galaxy. Its relatively unimpeded line of sight lets telescopes like Keck and space-based infrared observatories gather data on its dust spiral, orbital dynamics, and colliding winds with unparalleled clarity. Even minor changes in the system can be detected over a span of years or decades, allowing for long-term studies of how massive binaries evolve and how Wolf-Rayet stars lose mass before their ultimate demise. Its proximity provides both a literal and metaphorical window into one of the most extreme forms of stellar life. Moreover, the Pinwheel Star's location in the galactic plane adds to its significance. Situated among other massive stars and remnants of previous stellar generations, it contributes to the ongoing cycle of stellar evolution in our region of the Milky Way. Its stellar winds enrich the interstellar medium with heavy elements, and the eventual supernova will further disperse these materials, potentially seeding nearby regions with the building blocks of future stars and planets. At 8,000 light-years, the Pinwheel Star is close enough that we can study this enrichment process in detail, giving scientists critical insights into how massive stars shape the chemical evolution of our galaxy. The concept of proximity also affects our perception of risk and awe. Knowing that the Pinwheel Star is near enough to theoretically influence Earth heightens the sense of wonder and respect for its power. While the threat has been greatly reduced by studies revealing the system's orbital tilt, the fact remains that we are observing a star that is relatively close, spinning a spiral of dust, and preparing for an explosive future. This proximity turns the Pinwheel Star from a distant curiosity into a tangible example of the universe's scale, energy, and potential impact on life. It bridges the gap between abstract astrophysics and human experience, reminding us that even on a galactic scale, distance can matter. Gamma-ray bursts, or GRBs, are often described as the most powerful explosions in the known universe, and when discussing the Pinwheel Star, they loom large as both a fascination and a fear. To fully appreciate the significance of the Pinwheel Star's potential threat, it's essential to understand what GRBs are, how they form, and why they are so catastrophic in their effects. A gamma-ray burst is an extremely energetic flash of gamma radiation, lasting anywhere from a fraction of a second to several minutes. During this brief window of time, a GRB can release more energy than our Sun will emit over its entire 10 billion year lifetime. These bursts are so luminous and so powerful that they can be detected across billions of light years, making them one of the few cosmic events we can observe from the farthest reaches of the universe. There are two primary categories of GRBs: short duration bursts and long duration bursts. Short GRBs, typically less than 2 seconds long, are thought to be caused by the mergers of neutron stars or a neutron star with a black hole. Long GRBs, which can last from a few seconds to several minutes, are generally associated with the collapse of massive stars, stars like the Pinwheel Star in its Wolf-Rayet phase. In the case of long GRBs, the physics behind them is as extraordinary as it is terrifying. When a massive star exhausts its nuclear fuel, the outward pressure that counteracts gravity disappears, causing the star's core to collapse. If the star is rotating rapidly and has stripped away its outer layers, as is the case with Wolf-Rayet stars, the collapse can channel energy into focused jets that blast outward from the star's rotational poles. These jets are composed of gamma radiation and ultra-relativistic particles moving at nearly the speed of light. If such a jet happens to be pointed directly at Earth, even from thousands of light years away, it could wreak havoc on our planet's atmosphere. The catastrophic potential of a GRB lies in its interaction with planetary atmospheres. Gamma rays themselves would not directly incinerate life on the surface, but they would strip away the protective ozone layer that shields the planet from harmful ultraviolet radiation from its parent star. Without the ozone layer, the surface would be bombarded by intense UV radiation, leading to widespread destruction of ecosystems. Plants and phytoplankton, the foundation of most food chains, would be severely damaged, causing cascading collapses in biodiversity. Moreover, GRBs could trigger the formation of nitrogen oxides in the atmosphere, leading to acid rain and further environmental devastation. In short, a GRB aimed at Earth could result in a mass extinction event, even if the burst occurred thousands of light years away. Evidence suggests that GRBs may have played a role in Earth's past extinctions. Some researchers hypothesize that the Ordovician Silurian extinction event, which wiped out much of Earth's marine life around 450 million years ago, could have been triggered by a gamma-ray burst. While this idea remains speculative, it highlights the very real possibility that GRBs have influenced the course of life on Earth before and could potentially do so again. The mere idea that such a distant astrophysical event could profoundly alter life on our planet underscores the immense power of these cosmic explosions. Adding to their danger is the fact that GRBs are narrowly beamed. Unlike a supernova, which radiates energy in all directions, a GRB is highly directional, with jets confined to a small angle, sometimes only a few degrees across. This makes them rare in terms of directly impacting a planet, but it also means that if Earth happened to fall within the line of fire, the damage would be immense. The narrow beam is both a relief and a source of tension. It greatly reduces the odds of Earth ever being hit. But if the Pinwheel Star were aligned with us, its eventual collapse could spell disaster, despite its distance of 8,000 light-years. For decades, astronomers viewed the Pinwheel Star with apprehension, because it fit many of the conditions required to produce a long-duration GRB. It is a massive Wolf-Rayet star. It has shed its outer layers, and it spins with enough angular momentum to potentially generate polar jets upon collapse. When its spiral was first observed nearly face-on, the concern was that this might mean its axis, and therefore any potential GRB was aimed directly at Earth. This was why the Pinwheel Star was briefly nicknamed a Death Star in popular media. Although later studies relieved much of this fear, the association between the Pinwheel Star and GRBs has never truly disappeared, because it remains an ideal candidate for such an event in theoretical astrophysics. But while their destructive potential is terrifying, GRBs are also invaluable to science. They serve as cosmic lighthouses, allowing astronomers to probe the distant universe. Because they are so bright, they can be seen billions of light years away, acting as markers for the deaths of the first generations of massive stars. Studying GRBs gives insight into the early universe, the formation of black holes, and the mechanisms of extreme physics that cannot be replicated in laboratories on Earth. The very same phenomenon that could devastate life is also one of the most important tools for expanding our knowledge of the cosmos. The Pinwheel Star, being relatively nearby, gives us a rare chance to study the kind of progenitor system that could produce a GRB. By examining its winds, its spiral, and its orbital dynamics, scientists can refine their models of how GRBs form, how likely they are to occur, and how their jets might behave as they propagate through space. While we now know that Earth is not in the direct line of fire, the Pinwheel Star remains a living laboratory for understanding one of the universe's most extreme and destructive events. Its proximity ensures that we can study it in unprecedented detail, but it also ensures that we never forget what is at stake when dealing with gamma-ray bursts, the raw, unfiltered power of the cosmos, capable of reshaping life itself across vast stretches of space. When the Pinwheel Star was first studied in detail, its elegant spiral was more than just an astronomical wonder. It carried an unsettling implication. Astronomers realized that the spiral pattern wasn't just a two-dimensional image painted across the heavens. It revealed orientation, an alignment in three-dimensional space that made people sit up and take notice. The spiral suggested that Earth might be staring straight down the barrel of the star's eventual fate. Wolf-Rayet stars, like the Pinwheel Star, are candidates for some of the most powerful explosions in the universe. When they collapse, they don't always explode in every direction equally. Instead, in some cases, the collapse produces narrow beams of radiation called gamma-ray bursts. These bursts don't fan out across the cosmos, but focus their destructive energy into tight cones that can travel vast distances without losing much of their punch. If a planet sits in the path of that cone, distance becomes less of a shield. Even thousands of light years away, a well-aimed gamma-ray burst could devastate the delicate balance of life. So when astronomers traced the graceful loops of the Pinwheel Star's spiral and realized it looked like it was oriented directly at us, alarms were raised. To the human eye, it was like looking down a rifle barrel, stunning, symmetrical, and potentially aimed at Earth. The thought was chilling. A star 8,000 light-years away could someday unleash a beam of radiation powerful enough to strip away the ozone layer, ignite chemical reactions in the atmosphere, and cause mass extinctions without ever coming physically close. This possibility quickly spread beyond the scientific community into popular media, sparking sensational headlines. People asked, "Is there a ticking time bomb in the constellation Sagittarius, quietly waiting to end life on Earth?" For a time, the Pinwheel Star wasn't just an astronomical curiosity, it was a spectre of cosmic doom. But science thrives on careful re-examination. The initial scare was based on limited data and early models that assumed the spiral's face-on appearance meant direct alignment. Later studies refined this picture, showing that orientation is trickier to judge from afar. The Pinwheel Star may look like it's pointing straight at us, but appearances can be deceiving. Even a small tilt in its axis, a few degrees in either direction, would mean that any eventual gamma-ray burst would miss Earth entirely. Still, the early scare served an important purpose. It forced scientists to think seriously about the risks of gamma-ray bursts and to refine their models of how these stellar explosions unfold. It also brought public attention to the raw power of the cosmos, reminding us that we live in a universe filled with forces far beyond our control, where beauty and danger often exist side by side. In the early 2000s, the Pinwheel Star was at the center of a scientific and public storm because of what its spiral seemed to imply. Astronomers had identified the star as a Wolf-Rayet type, with a massive OB companion, locked in a tight 8-month orbit. The binary system's dynamics were already fascinating, but the spiral of dust and gas, expelled by the colliding winds, presented an additional puzzle. Observed in infrared, the spiral appeared almost perfectly face-on, an orientation that raised a chilling possibility. Could the rotational axis of the star, the axis along which a gamma-ray burst would be emitted during a supernova, be pointing directly at Earth? This was the foundation of what became known as the alignment theories. These early theories were rooted in a combination of observational data and astrophysical modeling. When the spiral was first imaged, its symmetry suggested that we were looking down the rotational pole of the Pinwheel Star. Because gamma-ray bursts are highly collimated events, aligned along the rotational axis of the collapsing star, this initial interpretation triggered a cascade of speculation. If the axis truly was directed toward Earth, and if the Pinwheel Star ended its life as a long-duration gamma-ray burst, the consequences could be catastrophic, even though the star was approximately 8,000 light-years away. This scenario was particularly concerning because Wolf-Rayet stars are considered some of the most likely progenitors of gamma-ray bursts due to their stripped outer layers and rapid rotation. The foundation of these alignment theories relied heavily on the spiral's geometry and the physics of colliding stellar winds. In a binary system, the winds from each star collide, compressing and heating the gas, which then forms dust. This dust is expelled along paths determined by the orbital dynamics of the binary system. When viewed from Earth, the spiral can appear face-on or edge-on, depending on the orientation of the system's orbital plane relative to our line of sight. Early measurements, constrained by the resolution limits of infrared telescopes at the time, suggested a nearly face-on spiral. This observation was interpreted by some researchers as an indicator that the star's rotational pole, the likely axis of any potential gamma-ray burst, was aligned toward Earth. One of the reasons this theory gained traction was the recognition that the Pinwheel Star fit many of the conditions thought necessary for a gamma-ray burst. It is a Wolf-Rayet star, meaning it has lost its outer hydrogen envelope and is composed of heavier elements like carbon and oxygen. This stripping process is critical for gamma-ray bursts because it allows any polar jets formed during core collapse to escape the star without being impeded by a thick outer layer. Additionally, the star is rapidly rotating, a factor that can focus the energy of a collapsing core into narrow, high-energy beams along its rotational poles. In other words, the Pinwheel Star had the right stuff to produce a gamma-ray burst if and when it collapsed. Further fueling the alarm was the proximity of the star. At 8,000 light-years, it is close enough for its light and other emissions to be resolved in detail, but close enough that a directed gamma-ray burst could, in theory, impact Earth. While most supernovae pose little risk at such distances because their energy is dispersed spherically, gamma-ray bursts behave differently. Their energy is focused into narrow jets, meaning that even a star thousands of light-years away could produce effects potent enough to disrupt the atmosphere and biosphere of a planet in the line of fire. This realization made the question of alignment not just a matter of curiosity, but a crucial factor in determining potential cosmic hazard. Scientists began modeling the possible orientation of the system using available data on the spiral's shape, its angular size, and the dynamics of dust formation in colliding winds. These models attempted to infer the inclination of the orbital plane and the orientation of the Wolf-Rayet star's rotational axis. The early models, limited by observational constraints, suggested that the system was oriented within a few degrees of a face-on view, lending credence to the notion that the star's rotational pole could indeed be pointing toward Earth. This created headlines and public concern, with the Pinwheel Star suddenly being portrayed as a potential Death Star in scientific and popular discussions alike. However, the alignment theories were always tentative because they depended on indirect inferences. Observing the orientation of a star thousands of light years away is extraordinarily difficult, and the appearance of the spiral alone could be misleading. For example, projection effects and three-dimensional twists in the spiral can make a system appear more face-on than it really is. Dust density variations, interactions with surrounding interstellar material, and subtle orbital eccentricities could all influence the observed shape of the spiral. Despite these uncertainties, the early alignment models played a crucial role in highlighting the potential risk posed by nearby Wolf-Rayet stars, bringing attention to the mechanisms of gamma-ray bursts and their impact on planets. The consequences of a potential alignment added a sense of urgency to these early theories. If the rotational pole of the Pinwheel Star were pointing at Earth, and if the star were to collapse in the coming thousands or millions of years, the resulting gamma-ray burst could have profound effects. Models indicated that the atmosphere could be stripped of protective layers, ultraviolet radiation could intensify at the surface, and widespread ecological damage could ensue. While these are long-term scenarios on human timescales, they are rapid and catastrophic on geological and biological timescales. This possibility gave the alignment theories a weight that extended beyond mere academic interest. It became a question of existential relevance, at least hypothetically. The debate surrounding the alignment of the Pinwheel Star also influenced observational priorities in astronomy. Telescopes such as the Keck Observatory and other infrared instruments were directed to study the system more precisely, focusing on spectral lines, dust distribution, and orbital parameters. The goal was to move beyond speculative interpretations and determine the actual inclination of the system's orbit. These studies eventually revealed that the initial fears, while understandable, were overstated. The system is tilted roughly 30 to 40 degrees away from Earth, meaning that any gamma-ray burst would almost certainly miss our planet. Nonetheless, the alignment theories served as a catalyst for these detailed studies, pushing the boundaries of what we could learn about this extraordinary star system. Interestingly, the early alignment models also prompted theoretical work on the mechanics of gamma-ray bursts themselves. By considering a real nearby candidate like the Pinwheel Star, astrophysicists could refine their understanding of how polar jets form, how stellar rotation influences jet direction, and how the distribution of surrounding material affects the propagation of a burst. In a sense, the Pinwheel Star became a case study in high-energy astrophysics, a tangible example that forced scientists to reconcile observational data with theoretical predictions about some of the universe's most violent phenomena. In addition, the public fascination with the alignment theories helped bridge the gap between abstract astrophysical concepts and general awareness. Articles, documentaries, and scientific outreach used the Pinwheel Star to illustrate the principles of stellar evolution, the nature of Wolf-Rayet stars, and the reality of cosmic hazards. The notion that a star's orientation in space could have consequences for life on Earth captured the imagination and underscored the importance of studying high-energy events on cosmic scales. It was a rare instance where an esoteric astronomical phenomenon resonated with existential concerns, making the Pinwheel Star both scientifically significant and culturally memorable. Ultimately, the early alignment theories surrounding the Pinwheel Star highlight the delicate interplay between observation, interpretation, and cosmic uncertainty. The near face-on appearance of the spiral initially suggested a direct threat, leading to understandable alarm. These theories, while later revised, underscored the potential impact of nearby Wolf-Rayet stars and emphasized the need for precise measurements in high-energy astrophysics. They also cemented the Pinwheel Star's reputation as one of the most mysterious and fascinating stars in our galaxy, a star whose beauty, complexity, and potential danger continue to captivate scientists and the public alike. The Pinwheel Star's allure lies not only in its spiraling beauty, but also in the latent power it harbors as a massive Wolf-Rayet star nearing the end of its life. Like all stars of its kind, the Pinwheel Star is in a stage of evolution that inevitably leads toward a spectacular death, a supernova. While the term supernova evokes images of explosive brilliance across the night sky, the stakes become far more tangible when combined with the potential of a gamma-ray burst. A supernova in isolation would be a dazzling cosmic event, but generally not catastrophic at 8,000 light-years. However, when a collapsing Wolf-Rayet star channels its energy into narrowly focused jets, the effects on Earth could be profound. The supernova risk associated with the Pinwheel Star centers on the mechanics of core collapse. When the nuclear fuel in the core of a massive star is exhausted, the outward pressure that counteracts gravity disappears, leading to an implosion of the core. In a star as massive and stripped down as the Pinwheel Star, this collapse can produce a black hole at the center. Under the right conditions, specifically if the star retains enough rotational speed and angular momentum, the collapsing core funnels energy into narrow jets along its rotational axis. These jets are composed of gamma radiation, particles moving near the speed of light, and intense magnetic fields. This is the mechanism behind a long-duration gamma-ray burst, one of the most energetic events in the universe. If such a burst were directed at Earth, the consequences could be catastrophic. The first effect would be the depletion of the ozone layer, our planet's primary shield against harmful ultraviolet radiation. Gamma rays interacting with the upper atmosphere generate nitrogen oxides, which catalyze the destruction of ozone molecules. Within hours to days, this could lead to widespread exposure of the biosphere to ultraviolet radiation, severely impacting photosynthetic organisms such as phytoplankton and terrestrial plants. Because these organisms form the base of the food chain, the collapse of primary productivity could cascade through ecosystems, potentially leading to mass extinctions. Beyond biological impacts, the chemical changes in the atmosphere could induce acid rain, alter climate patterns, and disrupt atmospheric circulation. The combination of UV radiation exposure, ecological collapse, and atmospheric alteration creates a scenario in which life on Earth could be profoundly affected without any physical contact from the star itself. The devastation would not be limited to one region. A gamma-ray burst can affect the entire hemisphere within its beam, and because Earth rotates, the impact would be distributed across global ecosystems. In essence, the planet's surface could experience a sudden and dramatic environmental shock. The supernova risk is compounded by the fact that gamma-ray bursts are narrowly focused. Unlike the isotropic explosion of a typical supernova, a GRB emits most of its energy in a tight cone that travels nearly unattenuated through space. This means that only planets lying within the path of the jet are at risk, which, on one hand, reduces the overall probability of impact, but, on the other, magnifies the consequences for any planet that happens to be in the line of fire. Even at a distance of 8,000 light-years, the intensity of a direct GRB could rival the output of the entire Sun for a brief but devastating period. The energy delivered would be enough to strip away protective layers, ionize the atmosphere, and trigger chemical reactions with long-lasting effects. Historical evidence and modeling suggest that such events, though rare, have the potential to influence the evolution of life on a planetary scale. Some mass extinction events in Earth's history may have been initiated or exacerbated by nearby gamma-ray bursts, though definitive proof remains elusive. The Pinwheel Star, by virtue of being relatively nearby and fitting the profile of a long-duration GRB progenitor, became a natural case study for understanding these possibilities. Researchers simulated scenarios in which a GRB targeted Earth from a distance comparable to that of the Pinwheel Star, illustrating how even brief exposure could result in global ecological disruption, atmospheric chemistry changes, and mass mortality among life forms. Despite these alarming potentials, it is important to contextualize the risk. The probability of the Pinwheel Star producing a gamma-ray burst aimed at Earth remains extremely low, particularly after studies refined the orientation of the system. Observations now indicate that the star's rotational axis is tilted approximately 30 to 40 degrees away from our line of sight, greatly reducing the likelihood of a direct hit. Nevertheless, the supernova risk remains a compelling area of study because it represents the extreme limits of what massive stars can do. Even without a direct GRB, the eventual supernova explosion will release immense energy and material into the surrounding interstellar medium, influencing star formation, chemical enrichment, and the dynamics of nearby stellar systems. The potential consequences also underscore the importance of understanding stellar evolution and the life cycles of massive stars. By studying the Pinwheel Star and other Wolf-Rayet systems, astronomers can refine models of core collapse, jet formation, and gamma-ray burst mechanics. These insights have broader implications for predicting the frequency and distribution of high-energy events across the galaxy, assessing risks to planets, and understanding the role of such catastrophic processes in shaping galactic ecology. In this sense, the Pinwheel Star is both a warning and a laboratory, offering a window into the extreme physics that govern the death of massive stars. Furthermore, the supernova risk highlights the interconnectedness of cosmic phenomena and life on Earth. While humans cannot influence the fate of distant stars, understanding these processes informs planetary defense strategies, guides astrophysical research priorities, and cultivates a deeper appreciation for the fragility and resilience of life. The Pinwheel Star, with its potential to produce a catastrophic gamma-ray burst, exemplifies the thin line between cosmic beauty and destructive power. Its eventual demise will be both a scientific milestone and a stark reminder of the forces at play in the universe, forces capable of shaping, altering, or even extinguishing life on planets across light years of space. After years of concern over the Pinwheel Star, a wave of relief swept through the astronomical community thanks to detailed observations from the Keck Observatory. Using high-resolution spectroscopy and advanced infrared imaging, astronomers were finally able to resolve the long-standing uncertainty about the system's orientation. The findings revealed that the binary orbit of the Pinwheel Star is tilted approximately 30 to 40 degrees away from Earth, dramatically reducing any realistic risk of a gamma-ray burst being directed at our planet. This discovery transformed the Pinwheel Star from a hypothetical death sentence into a safe, yet still fascinating, celestial object. The implications of this tilt are profound. Gamma-ray bursts, as highly focused beams of energy, are lethal only when their narrow jets align directly with a target. In the case of the Pinwheel Star, the combination of its orbital tilt and the orientation of its rotational axis means that any future GRB is extremely unlikely to intersect with Earth. While the star remains a potential progenitor of a GRB, one of the most energetic events in the cosmos, this new data effectively rules out the immediate threat that had once captured both scientific and public imagination. What once appeared to be a cosmic sniper aimed at our planet has now been shown to be pointing well off target. The methodology behind these findings is a testament to the power of modern astronomy. By examining subtle spectral shifts in the light emitted by the Pinwheel Star system, researchers could measure the Doppler effect caused by the motion of the two stars in their tight 8-month orbit. The velocity patterns observed in the spectral lines allowed scientists to model the three-dimensional orientation of the orbit with unprecedented accuracy. Combined with infrared imaging of the iconic dust spiral, these measurements provided the evidence necessary to determine that the system is tilted, and that the previously perceived face-on appearance was an optical illusion influenced by perspective and the geometry of the spiral itself. This discovery not only alleviates fears, but also opens new scientific avenues. With the threat of a direct GRB largely eliminated, researchers can now focus on understanding the Pinwheel Star for what it truly is: an extraordinary laboratory for studying massive star evolution, colliding stellar winds, and dust formation in extreme environments. The system offers insights into how Wolf-Rayet stars shed mass and enrich the interstellar medium, which has implications for understanding the chemical evolution of galaxies. The tilted orientation also raises intriguing questions about why the spiral appears almost face-on, despite the orbital inclination, a puzzle that continues to drive observational and theoretical work. The reprieve has broader implications for astrophysics as well. The Pinwheel Star serves as a cautionary tale about interpreting observational data, particularly when judging potential cosmic hazards. Early assumptions about the system's alignment were reasonable given the data available at the time, but they also highlight how limited resolution and perspective effects can lead to alarming conclusions. Modern instruments, capable of resolving fine spectral details and imaging structures at unprecedented clarity, now allow for more accurate modeling, underscoring the importance of continually refining our understanding of the universe as technology advances. For the general public, the news of the orbital tilt transformed the narrative around the Pinwheel Star. Media outlets that once sensationalized the star as a Death Star began to emphasize its beauty, its scientific value, and the awe-inspiring complexity of the spiral. While the sense of existential threat diminished, fascination remained. People could now appreciate the Pinwheel Star as a cosmic marvel, a vivid demonstration of stellar dynamics and the violent but orderly processes that govern massive binary systems, without the accompanying fear of imminent destruction. The Keck findings also illustrate the interplay between theoretical prediction and empirical observation. Models of gamma-ray bursts and Wolf-Rayet evolution predicted certain behaviors and potential risks, but without precise measurements of orientation, these predictions remained speculative. By confirming the orbital tilt, astronomers could finally calibrate their models more accurately, reducing uncertainties about the likelihood of catastrophic GRBs from nearby massive stars. This has repercussions not only for the Pinwheel Star, but also for our broader understanding of gamma-ray burst progenitors throughout the galaxy. Importantly, the tilt does not diminish the Pinwheel Star's dramatic life story. Wolf-Rayet stars are inherently unstable, and the system will eventually undergo a supernova explosion. The difference is that, thanks to the tilt, Earth will almost certainly be spared from direct harm. This allows researchers to study the star with a focus on the astrophysical processes themselves, rather than on potential planetary consequences. Observing the evolution of such a system in real time provides rare insights into the late stages of massive star evolution, the dynamics of colliding winds, and the mechanisms behind dust spiral formation. In short, the recent reprieve does more than just relieve existential anxiety. It shifts the focus from fear to discovery. The Pinwheel Star can now be appreciated as one of the most spectacular and informative astronomical laboratories in the Milky Way. Scientists continue to monitor its dust spiral, orbital dynamics, and stellar wind interactions, seeking answers to questions about mass loss, binary evolution, and the precise mechanisms that could one day produce a gamma-ray burst. While the danger is now considered highly unlikely, the scientific intrigue remains as powerful as ever, making the Pinwheel Star a symbol of how even the most frightening cosmic phenomena can yield invaluable knowledge when observed with care and precision. With the new measurements confirming the orbital tilt of the Pinwheel Star, the relief among astronomers and the wider scientific community has been substantial. The fear that this nearby Wolf-Rayet star might one day unleash a gamma-ray burst aimed directly at Earth, a catastrophic event capable of obliterating the ozone layer and causing mass extinctions, has been largely allayed. The tilt, now estimated at 30 to 40 degrees away from our planet, makes a direct hit extraordinarily improbable. While the star will inevitably end its life in a supernova, the combination of its orientation and distance renders Earth essentially safe from the most extreme consequences of its demise. This sense of relief is not merely about avoiding a hypothetical apocalypse. It also represents a triumph of careful observation, modeling, and persistence in astronomical research. For years, the Pinwheel Star captured both scientific and popular imagination as a Death Star on a cosmic scale. Its near face-on dust spiral had suggested that the star's rotational axis, along which a gamma-ray burst would be emitted, was aligned with Earth. Given the immense energy released by such bursts, even a star thousands of light-years away could theoretically wreak havoc on our planet's atmosphere. Early models painted a scenario that, while statistically unlikely, was alarming enough to provoke serious discussion in both scientific journals and mainstream media. The relief comes from a combination of refined observational techniques and advanced computational modeling. Using high-resolution spectroscopy, astronomers were able to measure the Doppler shifts of the binary system, mapping the velocities of both stars in their tight orbital dance. By analyzing these shifts over time, researchers reconstructed the three-dimensional orientation of the binary orbit, revealing that the system is in fact tilted relative to Earth's line of sight. Combined with infrared imaging of the iconic dust spiral, these measurements demonstrated that the earlier fears of a direct GRB impact were based on a misleading visual perspective. What appeared to be a face-on orientation was actually a combination of projection effects and the geometry of the dust spiral rather than an indicator of imminent danger. The consequences of this re-evaluation are both scientific and philosophical. On one level, it allows astronomers to shift focus from speculative disaster scenarios to more constructive lines of inquiry. Instead of worrying about hypothetical annihilation, researchers can study the Pinwheel Star as a living laboratory for understanding the final stages of massive star evolution. Its colliding stellar winds, dust formation, and binary dynamics provide insights into the complex processes that govern Wolf-Rayet stars and their eventual explosive deaths. The star remains fascinating, but now without the existential shadow that once loomed over it. From a broader perspective, the relief underscores the importance of precision in astronomy. Early interpretations were based on the best available data at the time, yet they carried significant uncertainty. As observational technology advanced, astronomers were able to obtain more accurate measurements, highlighting the dynamic and evolving nature of scientific understanding. The Pinwheel Star serves as a cautionary tale about drawing conclusions from limited data, while simultaneously exemplifying how science self-corrects over time. What was once a potential threat has become a source of knowledge and inspiration. This newfound security also allows for more detailed and nuanced studies of the star's potential for producing gamma-ray bursts in general. Scientists can now investigate the mechanisms behind jet formation, stellar wind interactions, and binary evolution without the distraction of an imminent planetary threat. The system's tilt offers a natural laboratory for testing models of long-duration GRBs in conditions where the effects on Earth are negligible. By observing a relatively nearby candidate, researchers can refine predictions about GRB frequencies, energy distributions, and environmental consequences, improving our understanding of these rare but highly energetic events across the galaxy. Public perception has similarly shifted. Whereas the Pinwheel Star once captured headlines as a looming existential threat, it is now celebrated for its beauty, complexity, and scientific value. The awe-inspiring spiral, which initially triggered concern due to its orientation, can now be appreciated without the anxiety of potential destruction. This shift in narrative, from Death Star to cosmic marvel, demonstrates how evolving scientific knowledge reshapes our understanding of the universe and our place within it. The star remains an object of fascination, inspiring curiosity and wonder, but now with reassurance rather than fear. Importantly, the relief does not diminish the Pinwheel Star's status as one of the most extraordinary stellar systems known. Its colliding winds, dust spirals, and binary dynamics continue to provide critical data for understanding stellar evolution, chemical enrichment of the interstellar medium, and the conditions that give rise to extreme astrophysical phenomena. While Earth is no longer considered at risk, astronomers can study the system in greater depth, leveraging its proximity to refine models of mass loss, stellar rotation, and jet formation in massive stars. In this sense, the tilt has not only averted concern, it has unlocked new opportunities for scientific exploration. Ultimately, the story of the Pinwheel Star's perceived threat and subsequent reprieve illustrates a profound truth about the cosmos. The universe is both violent and beautiful, capable of awe-inspiring creation and destruction, yet our understanding of it continually evolves. By carefully measuring, modeling, and interpreting the signals from distant stars, scientists can separate myth from reality, fear from fact. The Pinwheel Star, once feared as a cosmic executioner, is now understood as a nearby laboratory of stellar physics, a symbol of both the power and precision of modern astronomy, and a reminder that even the most mysterious objects in the universe can ultimately be approached with both caution and curiosity. Even after the relief regarding the Pinwheel Star's potential threat, astronomers have found themselves captivated by a new puzzle: the appearance of its iconic dust spiral. Infrared images reveal a near-perfect face-on spiral that seems almost geometrically aligned with our line of sight, giving the impression that we are looking directly down the rotational pole of the system. This is particularly striking because, as later measurements revealed, the orbital plane of the Pinwheel Star is tilted roughly 30 to 40 degrees away from Earth. The apparent contradiction, an orbit inclined at a significant angle, yet a spiral that appears nearly face-on, has become a source of intrigue and a driving question for modern astrophysical research. Understanding why this apparent misalignment occurs requires a deeper dive into the dynamics of colliding stellar winds. In binary systems like the Pinwheel Star, the Wolf-Rayet star and its OB companion emit powerful stellar winds that collide at supersonic speeds. These collisions compress and heat the gas, leading to the formation of dust, which is then carried outward in a spiral pattern by the orbital motion of the stars. In theory, the orientation of this spiral should roughly correspond to the inclination of the orbital plane. However, the observed near face-on appearance suggests that other factors may be at play, distorting the expected geometry. One possibility is the effect of projection. Three-dimensional structures can appear dramatically different when viewed from a particular angle. A spiral that is physically inclined relative to Earth might still project onto the sky as an almost circular face-on pattern if certain geometric conditions are met. In the case of the Pinwheel Star, variations in the density, speed, and direction of the stellar winds could exaggerate this effect. For example, if the dust is preferentially concentrated along specific portions of the spiral due to wind interactions, it might create an optical illusion of a more face-on structure than the underlying orbital plane would suggest. Another contributing factor could be the role of precession. Binary star systems are not rigid. Gravitational interactions between the stars, coupled with mass loss from the Wolf-Rayet star, can cause the orbital plane to wobble or precess over time. This precession can influence the orientation of the dust spiral as it propagates outward, creating patterns that do not perfectly trace the instantaneous orbital plane. If the Pinwheel Star's orbit has experienced precession over hundreds or thousands of years, the outer portions of the spiral could retain a geometry that appears closer to face-on, even if the inner orbit is inclined relative to Earth. The physical properties of the dust itself may also play a role. Dust grains in the Pinwheel Star's spiral are composed of complex molecules formed under extreme conditions of temperature and pressure. The interaction between radiation pressure from the stars and the momentum of the colliding winds can influence the trajectories of these grains, potentially creating a spiral morphology that exaggerates circular symmetry when viewed from Earth. Additionally, the formation of dust is not uniform. Clumping or variability in the density of dust along the spiral arms can emphasize certain features while diminishing others, contributing to the apparent face-on effect. Spectroscopy has added further layers to the mystery. By analyzing the light emitted and absorbed by the dust and gas in the system, astronomers can infer velocities, temperatures, and chemical composition at various points in the spiral. These measurements sometimes reveal inconsistencies with the simple geometric models of a uniformly expanding, orbitally aligned spiral. Such discrepancies suggest that additional processes, perhaps turbulence in the colliding winds, magnetic fields, or interactions with surrounding interstellar material, are influencing the shape and appearance of the spiral. The near face-on appearance also raises questions about observational biases. Most of our high-resolution images of the Pinwheel Star come from infrared telescopes capable of detecting thermal emission from dust. Infrared emission is sensitive to temperature and density, which means that regions of the spiral that are warmer or denser appear brighter, while cooler or more diffuse areas are less visible. This selective brightness can make the spiral appear more circular or symmetric than it truly is, further complicating attempts to match observational images with the known orbital tilt. This discrepancy between appearance and measured orientation has transformed the Pinwheel Star from a simple case study into a rich, multidimensional problem in astrophysics. Researchers are now using sophisticated three-dimensional hydrodynamic simulations to model how the interplay of stellar winds, orbital motion, precession, and dust formation produces the observed spiral. These simulations aim to replicate not just the overall shape, but also the detailed brightness distribution observed in infrared imaging. By comparing models with observations, astronomers hope to uncover the hidden physics that govern the system and resolve the apparent paradox of a face-on spiral emerging from a tilted orbit. In addition to its intrinsic scientific interest, this mystery has broader implications for our understanding of massive star systems. If projection effects, precession, or wind dynamics can create apparent discrepancies between orbital inclination and observed spiral geometry in the Pinwheel Star, similar effects might be present in other Wolf-Rayet binaries. This realization prompts astronomers to re-examine other dusty Wolf-Rayet systems and reconsider how orbital orientation is inferred from dust spirals alone. The Pinwheel Star thus serves as a benchmark for refining observational techniques and modeling strategies across the field. Ultimately, the face-on appearance of the Pinwheel Star's spiral, despite its tilted orbit, exemplifies the complexity of astrophysical systems. Even when a star has been studied extensively and its threat to Earth has been largely dismissed, it can still present entirely new enigmas that challenge existing theories. This ongoing puzzle reinforces why the Pinwheel Star remains one of the most intriguing objects in the galaxy. Its spiral is not merely a beautiful pattern in the cosmos, but a dynamic record of extreme physical processes, a laboratory for studying binary interactions, and a mystery that continues to inspire further exploration and discovery. The revelation that the Pinwheel Star's orbit is tilted roughly 30 to 40 degrees away from Earth did not come from a single observation, but from a careful combination of spectroscopy, imaging, and modeling, an intricate dance of data interpretation that underscores the sophistication of modern astronomy. Spectroscopy, in particular, played a central role in unraveling the true orientation of this remarkable system, providing a window into the velocities, motions, and interactions of the two stars in ways that direct imaging alone could not achieve. At its core, spectroscopy is the science of analyzing light to determine the properties of its source. When applied to a binary system like the Pinwheel Star, astronomers can measure the Doppler shift of spectral lines, the slight changes in wavelength caused by motion along our line of sight. If a star is moving toward Earth, its spectral lines are blue shifted. If it is moving away, they are red shifted. By tracking these shifts over time, particularly across multiple orbital cycles, astronomers can construct detailed velocity curves for both components of the binary. These curves reveal not just the speed of the stars, but the geometry of their orbital dance. For the Pinwheel Star, these velocity measurements were instrumental in determining the inclination of the orbit. By analyzing the amplitude and shape of the velocity curves, researchers could infer the angle at which the binary system is tilted relative to our viewpoint. Larger observed velocity variations correspond to orbits viewed edge-on, while smaller variations indicate more face-on orientations. The precise data from high-resolution spectrographs attached to telescopes like Keck allowed astronomers to discern subtle differences in velocity over the 8-month orbital period, ultimately revealing the tilt that had eluded earlier observations. In addition to velocity measurements, spectroscopy provided insight into the composition and behavior of the stellar winds themselves. Wolf-Rayet stars emit extremely fast, dense winds rich in heavy elements such as carbon, nitrogen, and oxygen. By examining emission and absorption lines in the spectra, astronomers could model how these winds interact with those from the OB companion. The colliding winds create complex shock fronts and zones of compressed material, which in turn influence the formation and outward flow of dust. Spectroscopic data allowed researchers to map these interactions in 3 dimensions, offering additional clues about the orbital geometry. For example, variations in line strength and shape over time provided evidence for the changing viewing angle of the colliding wind region as the stars orbited each other. Infrared imaging complemented these spectroscopic findings. While spectroscopy reveals the motion and physical properties of the stars and gas, infrared observations trace the dust itself, highlighting the spiral pattern created by the orbital motion and colliding winds. By combining the shape, pitch angle, and expansion rate of the spiral with the velocity data from spectroscopy, astronomers could construct a self-consistent 3-dimensional model of the system. The result confirmed that, although the spiral appears nearly face-on, the underlying orbit is indeed tilted relative to Earth's line of sight. This combination of techniques, tracking both the gas motions and the resulting dust morphology, was crucial for resolving the discrepancy between appearance and orientation. The spectroscopic data also allowed scientists to refine estimates of other critical parameters, such as the mass of each star, the speed of their stellar winds, and the orbital eccentricity. These parameters feed directly into models of stellar evolution and potential gamma-ray burst production. By knowing the orbital tilt, astronomers can more accurately predict the likelihood of any jet being directed toward Earth and simulate the dynamics of the dust spiral as it evolves over time. Without the detailed spectroscopic analysis, these models would remain speculative, and early concerns about a direct GRB threat would continue to cast a shadow over our understanding of the system. The process of determining the tilt also illustrates the iterative nature of astrophysical research. Early observations suggested a face-on spiral, prompting concern and theoretical speculation. Subsequent spectroscopy provided the quantitative data needed to challenge these assumptions. Advanced modeling then reconciled the data with the observed spiral morphology, revealing that projection effects and wind dynamics could create the illusion of a face-on pattern even when the orbit is inclined. This interplay between observation, measurement, and modeling exemplifies the scientific method at its best. Initial impressions are tested, challenged, and refined to produce a deeper understanding. Beyond the specific case of the Pinwheel Star, the methods used to determine its tilt have broader applications in astrophysics. Spectroscopic analysis of velocity curves is a cornerstone technique for studying binary systems, exoplanet detection, and stellar dynamics. By applying these techniques to a system as complex and luminous as the Pinwheel Star, astronomers refine their tools and models, gaining insights that can be applied to other Wolf-Rayet binaries and high-energy stellar systems. The ability to disentangle orbital motion, stellar wind interactions, and dust formation from spectroscopic data alone demonstrates the remarkable precision that modern instruments can achieve, even for objects thousands of light years away. The confirmation of the orbital tilt also brings with it an element of cosmic humility. Despite the apparent simplicity of the spiral's face-on projection, the underlying reality is far more complex, shaped by three-dimensional motions, colliding winds, and dust physics. It is a reminder that appearances in the night sky can be deceiving, and that only through careful, methodical measurement can astronomers uncover the true nature of celestial objects. Spectroscopy, in this case, served as the key to unlocking a deeper understanding, turning an apparent existential threat into a source of scientific insight. In summary, the science behind the tilt of the Pinwheel Star is a triumph of modern observational astrophysics. Spectroscopy provided the velocity data necessary to reconstruct the three-dimensional orbital geometry, while infrared imaging of the dust spiral validated and refined the models. Together, these techniques revealed that the orbit is tilted 30 to 40 degrees relative to Earth, effectively eliminating the possibility of a direct gamma-ray burst impact. Yet the work did more than provide reassurance. It offered a detailed window into the complex interplay of massive stars, stellar winds, and dust formation, demonstrating that even the most elegant and seemingly straightforward cosmic structures can conceal intricate underlying dynamics. The Pinwheel Star, once feared for its potential to harm our planet, now stands as a symbol of the precision and power of modern astronomy, a beautiful and mysterious system whose secrets are only beginning to be fully understood. The ultimate fate of the Pinwheel Star is written in the language of cosmic time, a scale so vast that human lifespans and even the history of civilization pale in comparison. Though the immediate threat to Earth has been alleviated by the confirmed tilt of its orbit, the star remains a ticking clock in astronomical terms, destined to end its life in a supernova explosion. But when exactly that event will occur is a question that encompasses thousands, tens of thousands, and potentially millions of years, depending on a variety of factors inherent to the physics of massive stars. The Pinwheel Star, as a Wolf-Rayet object, has already passed the main sequence phase of its life. It has shed most of its hydrogen envelope, leaving behind a core rich in helium and heavier elements. Stars of this type are essentially exposed nuclear furnaces, burning helium, carbon, and heavier nuclei at prodigious rates. Because the rate of fusion in Wolf-Rayet stars is incredibly high, their remaining lifespans are correspondingly short on a cosmic scale. Estimates suggest that the Pinwheel Star has only tens to hundreds of thousands of years left before its core can no longer sustain nuclear fusion, triggering gravitational collapse. Yet short, in cosmic terms, is relative. While tens of thousands of years may seem long compared to a human lifespan, it is virtually instantaneous in the 13.8 billion year history of the universe. During this time, the star continues to emit intense stellar winds, generating dust spirals and enriching the surrounding interstellar medium with heavy elements like carbon, nitrogen, and oxygen. These winds slowly strip away remaining material, gradually modifying the mass distribution and angular momentum of the system. Such changes, though subtle, influence the timing and nature of the star's ultimate explosion. The timeline for a potential gamma-ray burst adds another layer of complexity. Not every Wolf-Rayet supernova produces a GRB. Only those with sufficient rotation and mass alignment along the star's rotational axis can form the highly focused relativistic jets that constitute a gamma-ray burst. For the Pinwheel Star, even if these conditions are met, the tilt of its orbit means that the jet would likely miss Earth entirely. Nevertheless, the physical processes leading to jet formation, the collapse of the iron core, the formation of a black hole or neutron star, and the funneling of energy along the rotational poles must all occur within a relatively narrow window during the star's final evolutionary stage.
This stage could be as brief as a few minutes to hours in terms of observable energetic events, but it is preceded by thousands of years of preparatory evolution, including internal structural adjustments and mass loss through stellar winds.
Astrophysicists use models of massive star evolution to estimate the timing of these events. By analyzing the Pinwheel Star's current mass, rotation rate, and chemical composition, researchers can simulate its remaining lifetime, including the onset of core collapse and potential GRB conditions. These models suggest that the supernova could occur any time within the next 10,000 to 100,000 years, though uncertainties in mass loss rates, rotation, and binarity mean that this estimate could stretch to several 100,000 years. In the broader perspective, this is an ephemeral moment in the life of the galaxy, yet it represents a cataclysmic transformation for the star itself. Even after the initial supernova, the consequences of the explosion will ripple across space for thousands of years. Shock waves will propagate through the surrounding interstellar medium, compressing gas clouds and potentially triggering new star formation. Heavy elements ejected by the supernova will seed nearby regions with the building blocks for planets, life, and future generations of stars. In this sense, the timeline of the Pinwheel Star's fate is not just about the immediate explosive event, but also about the long-term influence it will exert on its cosmic neighborhood. Its death will be both an end and a beginning, a transformation that will resonate across tens of thousands of light years. Understanding these timelines is crucial for contextualizing the star's role in the galaxy. While humans cannot experience the supernova firsthand, studying stars like the Pinwheel Star allows astronomers to test models of stellar evolution and explosion dynamics. By examining its mass loss, rotation, and dust production today, scientists can better predict the conditions under which massive stars produce supernova and gamma-ray bursts. These insights inform our understanding of similar events throughout the Milky Way and in other galaxies, helping to map the life cycles of the most massive stars in the universe. Importantly, even if a gamma-ray burst were to occur, the timeline suggests that it is a concern for future generations of life, if life persists on Earth for hundreds of thousands of years. This perspective emphasizes the enormity of cosmic timescales and the rarity of events that can directly impact a planet from such vast distances. While the Pinwheel Star's explosive potential is awe-inspiring, its temporal distance from our present moment allows scientists and the public alike to admire its beauty and complexity without immediate existential fear. In short, the timelines of fate for the Pinwheel Star are measured in thousands to hundreds of thousands of years, with the supernova explosion and any potential gamma-ray burst occurring at a scale that dwarfs human experience. Its remaining life is fleeting in stellar terms, yet long enough to continue enriching our understanding of astrophysics, from stellar winds and binary dynamics to the formation of dust spirals and the mechanics of core collapse. The star's eventual death will be a defining moment in its cosmic neighborhood, but for now, it remains a luminous and enigmatic presence, spinning its mesmerizing spiral and quietly reminding us of the vast, patient rhythms of the universe. If the Pinwheel Star had been aimed directly at Earth, the scenario would have been nothing short of apocalyptic on a planetary scale. Gamma-ray bursts are the most energetic explosions in the universe, capable of releasing in seconds more energy than the Sun emits over its entire 10 billion-year lifetime. Unlike a supernova that radiates energy roughly isotropically, a gamma-ray burst channels almost all of its energy into narrow relativistic jets. If Earth were positioned within the path of such a jet, the consequences would be immediate and devastating, affecting the atmosphere, biosphere, and climate. The first and most critical impact would occur in the upper atmosphere. Gamma rays interacting with nitrogen and oxygen molecules trigger photodissociation and ionization reactions, generating large quantities of nitrogen oxides, NO and NO2. These compounds act as catalysts for the destruction of ozone, our planet's natural shield against ultraviolet radiation. A direct hit from a GRB originating from the Pinwheel Star's distance, roughly 8,000 light-years, could destroy a significant portion of the ozone layer within hours. This sudden depletion would expose life on the surface to extreme levels of UV radiation, causing massive die-offs in plants, phytoplankton, and other primary producers at the base of the food chain. The collapse of these foundational organisms would ripple upward, leading to widespread ecological disruption and potential mass extinctions. Beyond the immediate biological consequences, the atmospheric chemistry would undergo dramatic changes. The increase in nitrogen oxides could lead to the formation of nitric acid, resulting in acid rain capable of damaging freshwater ecosystems and soils over extended periods. The sudden influx of reactive nitrogen compounds could also alter the greenhouse properties of the atmosphere, leading to unpredictable climate effects. Some models suggest temporary cooling due to aerosol formation, followed by longer-term warming as atmospheric chemistry stabilizes, creating an unstable environment for surviving species. The effects on oceanic ecosystems would be particularly severe. Phytoplankton, which form the base of marine food webs and produce a significant portion of Earth's oxygen, are highly sensitive to UV radiation. A massive die-off could not only disrupt marine ecosystems, but also reduce global oxygen production temporarily, further stressing terrestrial and aquatic life. The cascading effects on fisheries, nutrient cycles, and carbon sequestration could be profound, potentially destabilizing Earth's climate and ecosystems for decades or even centuries. In addition to biological and chemical effects, the direct ionizing radiation from a GRB could pose a threat to any technology-dependent civilization. Satellites, power grids, and communication networks could be disrupted or destroyed by intense radiation and induced currents in the atmosphere. This would compound the environmental challenges with societal and infrastructural collapse, though of course such considerations are purely hypothetical and speculative. From a geological perspective, the Pinwheel Star's hypothetical GRB could be compared to some of the most severe extinction events in Earth's history. Researchers have speculated that gamma-ray bursts may have contributed to past mass extinctions, including events that wiped out significant fractions of marine and terrestrial life. The atmospheric consequences modeled in these scenarios mirror what would happen if the Pinwheel Star's jet had been aligned with Earth: ozone depletion, increased UV radiation, and cascading ecological collapse. In essence, life on Earth would be subjected to a global-scale environmental shock, unlike anything experienced in recorded history. The timescale of destruction would also be abrupt on evolutionary terms. While the star is 8,000 light-years away, gamma rays travel at the speed of light, meaning that once the burst reaches Earth, the initial atmospheric ionization and ozone depletion would occur within seconds to minutes. The ensuing ecological collapse would unfold over months to years, with recovery periods extending for decades or longer, depending on the severity of the ozone loss and ecosystem disruption. Even after the initial event, residual effects, such as climate perturbations and acid rain, could continue to influence planetary systems for extended periods. Interestingly, the hypothetical impact scenario underscores how incredibly sensitive life on Earth is to cosmic events. While massive stars are relatively rare, the universe is filled with potential GRB progenitors. The Pinwheel Star, in this hypothetical situation, illustrates the delicate balance between life on Earth and catastrophic astrophysical phenomena. It also emphasizes why understanding the orientation and evolution of nearby massive stars is not purely an academic exercise, but a crucial part of understanding long-term planetary habitability. The hypothetical consequences highlight that a single misalignment in the cosmic architecture, just a few degrees in the orientation of a relativistic jet, can mean the difference between life continuing undisturbed and catastrophic mass extinction. Had the Pinwheel Star's rotation axis been pointed toward Earth, even though it is thousands of light-years away, the consequences could have rivaled the most extreme extinction events in Earth's history. This underlines the extraordinary fortune of our planet's current position and the profound interplay between celestial mechanics and the survival of life. In summary, had the Pinwheel Star been aligned toward Earth, the outcome would have been catastrophic. Immediate atmospheric ionization, massive ozone depletion, and increased UV radiation would devastate life at the surface, beginning with microorganisms and plants, and cascading through ecosystems. Acid rain, climate perturbations, and oceanic disruptions would exacerbate the crisis, potentially resulting in mass extinctions. The event would be fast-acting in its initial impact, but leave lingering consequences for decades or centuries. This scenario, while thankfully hypothetical, provides a stark reminder of the enormous power of gamma-ray bursts and the delicate positioning of Earth in the galaxy, allowing life to persist despite the universe's inherent violence. The hypothetical devastation that a gamma-ray burst from the Pinwheel Star could inflict on Earth leads naturally to a broader, haunting question. Have cosmic gamma-ray bursts influenced the history of life on our planet? While direct evidence is elusive, researchers have long speculated that some of Earth's mass extinction events may have been triggered, or at least exacerbated, by the high-energy radiation of distant GRBs. Understanding this possibility requires examining both the mechanisms of GRB-induced destruction and the paleontological record, offering a contextual framework for evaluating the Pinwheel Star's past and potential cosmic impact. Gamma-ray bursts are incredibly rare in any given galaxy, yet their effects are extraordinarily powerful when Earth happens to lie in the path of a relativistic jet. Unlike more common astrophysical phenomena such as supernovae, which emit energy more evenly in all directions, GRBs concentrate their energy along narrow beams. If Earth intercepts one of these beams, the result is a focused deluge of gamma radiation capable of ionizing the upper atmosphere, depleting ozone, and flooding the surface with ultraviolet radiation. The consequences, atmospheric chemistry alterations, ecological collapse, and potential climatic shifts, mirror the effects described in the hypothetical scenario of the Pinwheel Star being aimed at Earth. Several mass extinction events in Earth's history have been scrutinized for potential connections to GRBs. For example, the Ordovician-Silurian extinction around 450 million years ago saw the loss of an estimated 85% of marine species. While traditionally attributed to glaciation and changes in sea level, some researchers have proposed that a nearby gamma-ray burst could have contributed to the extinction by depleting ozone and dramatically increasing UV radiation, particularly affecting marine phytoplankton. These primary producers form the base of the oceanic food web, and their sudden collapse could have triggered cascading ecological failures, amplifying the effects of environmental stresses already present. The late Devonian extinction, roughly 360 million years ago, is another candidate period where cosmic radiation may have played a role. Though multiple mechanisms, such as anoxia in oceans, volcanic activity, and climate change, have been implicated, researchers have speculated that a GRB could have exacerbated these stresses, pushing already vulnerable ecosystems past critical thresholds. The idea is that even if a gamma-ray burst was not the sole cause of an extinction event, its sudden and intense radiation could tip the balance toward widespread die-offs, particularly in sensitive marine environments and near-surface terrestrial ecosystems. Evidence for such events, however, is indirect. Unlike asteroid impacts, which leave distinctive iridium layers or craters, gamma-ray bursts do not leave clear physical markers in the geological record. Instead, scientists rely on modeling atmospheric and ecological consequences to infer plausibility. For instance, simulations of GRB impacts show that significant ozone depletion could last for years, accompanied by increased UV flux at the surface. Such conditions could induce DNA damage in many organisms, suppress photosynthesis in plants and phytoplankton, and lead to cascading ecosystem failures.
If these conditions coincided with other environmental stresses, it becomes plausible that a GRB might have contributed to a mass extinction. Interestingly, studies of isotopic anomalies in certain sediment layers provide tantalizing but inconclusive hints. Elevated levels of nitrates or shifts in carbon isotopes can be consistent with sudden changes in atmospheric chemistry and primary productivity, which are precisely the types of effects expected from a gamma-ray burst. While these signals are not definitive proof, they offer intriguing correlations that suggest GRBs could be one of several hidden drivers behind some of Earth's more enigmatic extinction events. Understanding the historical risk of GRBs also contextualizes our contemporary awareness of stars, like the Pinwheel Star. While the star is now known to be tilted away from Earth, eliminating immediate danger, the study of past potential GRB impacts underscores why astronomers were initially concerned. Massive Wolf-Rayet stars capable of producing gamma-ray bursts are rare, but their effects are so profound that even a single alignment with Earth could have catastrophic consequences. By comparing astrophysical data with paleontological evidence, scientists can better evaluate both the frequency and severity of GRB events over geological timescales, offering insight into the role that cosmic phenomena may have played in shaping life's evolutionary history.
Moreover, this contextualization highlights the precarious nature of life on Earth in the cosmic landscape. While asteroid impacts, volcanic eruptions, and climate shifts have all influenced evolution, GRBs represent an entirely different class of threat, one originating from the far reaches of the galaxy, instantaneous in effect, and largely invisible until it strikes. The potential historical impact of GRBs provides perspective on the Pinwheel Star's significance, reminding us that even distant stars can influence planetary habitability through their high-energy, end-of-life phenomena. In a sense, examining Earth's past in the context of cosmic gamma-ray bursts serves as a bridge between the Pinwheel Star's theoretical threat and the broader narrative of life's vulnerability in the universe. It is a humbling reminder that the survival of species on Earth has always been contingent, in part, on fortunate cosmic alignments. While the Pinwheel Star no longer poses a direct risk, its existence as a potential GRB progenitor serves as a living example of how the universe's most energetic and destructive processes have the power to shape life across vast distances and immense spans of time. Ultimately, this perspective adds layers to our understanding of the Pinwheel Star. The star is not merely a distant, beautiful spiral in the galaxy. It is a representative of a class of cosmic phenomena that may have influenced the trajectory of life on Earth in the deep past. Its presence invites reflection on both the fragility and resilience of ecosystems, the interplay of astrophysical and biological processes, and the remarkable fact that, despite the universe's capacity for destruction, life has endured. By considering the possibility that past extinctions may have been triggered by GRBs, we gain a richer appreciation for the significance of the Pinwheel Star and other Wolf-Rayet systems, not only as objects of scientific study, but also as markers of the profound interconnection between the cosmos and life on Earth. Even though the Pinwheel Star no longer poses a direct threat to Earth, astronomers remain intensely interested in watching it, not just as a potential progenitor of cosmic phenomena, but as a dynamic laboratory for understanding massive stars, binary interactions, and the creation of dust in extreme environments. Observing the Pinwheel Star requires cutting-edge technology, sophisticated modeling, and long-term commitment, because the system is both distant and extraordinarily complex. Its study exemplifies how modern astronomy combines multiple observational techniques to unlock the secrets of some of the most fascinating objects in the galaxy. Telescopes equipped with adaptive optics have been particularly valuable in observing the Pinwheel Star. Adaptive optic systems correct for the distortions caused by Earth's turbulent atmosphere, allowing ground-based telescopes to produce images with a clarity approaching that of space-based observatories. Using instruments at facilities such as the Keck Observatory in Hawaii, astronomers have been able to resolve the intricate spiral structure of the dust generated by the colliding stellar winds of the binary system. These observations allow researchers not only to monitor the evolution of the spiral over time, but also to infer physical properties such as wind velocities, mass loss rates, and orbital parameters. By capturing a sequence of high-resolution images over months and years, astronomers can watch the Pinwheel Star's dust spiral, rotate, and expand in real time, providing unprecedented insight into the mechanics of Wolf-Rayet binaries. Infrared imaging is another critical tool for studying the Pinwheel Star. The dust produced in the colliding winds absorbs stellar light and re-emits it at infrared wavelengths, which are invisible to the human eye but detectable with specialized instruments. Telescopes like the Very Large Telescope, VLT, and the Spitzer Space Telescope have been employed to capture this infrared emission, revealing the spiral structure in remarkable detail. These infrared observations complement spectroscopic data by tracing the movement and density of dust, allowing astronomers to create three-dimensional models of the outflow. By combining optical, infrared, and spectroscopic observations, researchers can build a comprehensive picture of how the Pinwheel Star generates and shapes its iconic spiral. Long-term monitoring of the system is crucial because changes in the orbital dynamics or wind interactions could alter the appearance and behavior of the spiral over time. Variations in wind speed or mass loss rate from either the Wolf-Rayet star or its OB companion can produce observable changes in the spiral's shape, density, and brightness. Additionally, precession or other orbital irregularities may gradually shift the orientation of the dust spiral, providing valuable data on the system's dynamics and the physics of binary evolution. Observing these subtle changes requires patience, precision, and coordination across multiple observatories worldwide, emphasizing the dedication of the astronomical community to studying such complex stellar systems. Spectroscopy continues to play a central role in watching the Pinwheel Star evolve. By analyzing the shifts in spectral lines over time, astronomers can track the radial velocities of both stars and the surrounding material, allowing them to refine models of the orbit, wind interactions, and eventual fate of the system. These measurements also provide insights into the chemical composition and temperature of the dust, as well as the rate at which material is ejected from the stars. Combined with imaging, spectroscopy allows astronomers to create dynamic, three-dimensional simulations of the system, making it possible to predict how the spiral and surrounding environment will evolve in the coming decades and centuries. Radio and X-ray observations add additional layers of understanding. Colliding winds in Wolf-Rayet binaries generate shocks that can accelerate particles to high energies, producing X-ray and radio emission. By monitoring these wavelengths, astronomers can probe the physics of the wind collision zone, gaining insight into temperatures, densities, and magnetic fields that are otherwise invisible in optical or infrared data. This multi-wavelength approach ensures a holistic view of the system, capturing the full range of energetic processes that govern its evolution. Space-based observatories are also invaluable because they eliminate the distortions of Earth's atmosphere and allow continuous monitoring at wavelengths that are partially or fully absorbed by our atmosphere. Instruments aboard telescopes like Hubble and the James Webb Space Telescope provide sharp images and spectra that can reveal fine structures within the spiral, the presence of clumps or asymmetries in the dust, and even subtle changes in brightness or composition over time. By combining these observations with ground-based efforts, astronomers achieve unprecedented temporal and spatial coverage, essential for studying the Pinwheel Star's dynamic behavior. The ongoing monitoring of the Pinwheel Star is not purely about observation for its own sake. It has significant scientific implications. Understanding how dust is produced and maintained in such extreme environments informs models of stellar evolution and chemical enrichment. Wolf-Rayet stars contribute heavy elements to the interstellar medium, and the dust produced in systems like the Pinwheel Star plays a critical role in the life cycle of galaxies, influencing star formation, planet formation, and even the potential for life in other systems. Watching the star allows scientists to see these processes in action, in real time, and to refine theoretical models based on empirical data. Astronomers are also using these observations to refine our understanding of supernova and gamma-ray burst progenitors. By studying the orbital dynamics, wind interactions, and rotational behavior of the Pinwheel Star, researchers can better predict the conditions under which such massive stars collapse and produce relativistic jets. This research not only improves our understanding of the Pinwheel Star itself, but also informs broader astrophysical questions, such as the frequency and distribution of gamma-ray bursts in the galaxy, their potential impact on planets, and the role of massive binaries in galactic evolution. The act of watching the Pinwheel Star carries an element of philosophical wonder. Observing its rotating dust spiral, tracking the delicate balance of forces in a binary system, and witnessing the interplay of stellar winds and gravity offers a profound reminder of the complexity and beauty of the universe. Even with the threat to Earth dismissed, the Pinwheel Star remains a source of mystery and fascination, a celestial dance that unfolds over months and years, yet encodes processes that operate over thousands to millions of years. By continuing to watch it, astronomers ensure that every photon, every spectral line, and every spiral arm contributes to our growing understanding of the cosmos, bridging the gap between raw observation and deep cosmic insight. The Pinwheel Star's spiral is more than a scientific object. It is a masterpiece of cosmic artistry, a luminous dance of matter and energy that captivates both the eye and the mind. Viewed through infrared imaging, the spiral coils outward in elegant arcs, tracing the orbital motion of the Wolf-Rayet star and its companion with mesmerizing precision. Each turn of the spiral is a record of the ongoing interaction between two stellar titans, colliding winds shaping dust, and gravity orchestrating a dynamic rhythm that has persisted for countless orbits. The sheer symmetry and regularity of the pattern evoke awe, illustrating the beauty that emerges from the extreme forces at play in the universe. Yet the Pinwheel Star's allure is not merely aesthetic, it is deeply scientific. The spiral provides a natural laboratory for exploring the physics of massive stars, binary evolution, and dust formation. Each curve encodes information about wind velocities, orbital motion, and mass loss rates, allowing astronomers to infer properties that would otherwise remain invisible across the vastness of space. Its apparent simplicity belies a complex interplay of hydrodynamics, radiation pressure, and orbital mechanics, making the star a rich source of data for testing models of stellar behavior. Observing the spiral is akin to reading a cosmic ledger, where every twist and brightness variation tells a story about the forces shaping the system. What makes this fusion of beauty and science particularly compelling is the way it transforms a formerly feared object into a subject of fascination. Once considered a potential Death Star, the Pinwheel Star now represents a safe but enigmatic phenomenon, inviting exploration rather than caution. Its study advances understanding not only of Wolf-Rayet binaries, but also of the broader mechanisms that govern stellar life cycles, supernovae, and even the conditions under which gamma-ray bursts form. The spiral, while visually striking, also serves as a practical tool for astronomers, offering direct insight into stellar processes in real time. This duality, where aesthetic wonder and scientific utility coexist, embodies the essence of astrophysics. The Pinwheel Star is simultaneously a spectacle to behold and a puzzle to solve, reminding us that nature's most beautiful creations often emerge from extreme and violent forces. Its spiraling dust bridges the gap between observation and theory, providing a tangible link between the cosmic artistry we perceive and the underlying physics that produces it. Ultimately, the Pinwheel Star stands as a symbol of discovery and curiosity. It reassures us that even the most potentially dangerous stars can reveal themselves as sources of knowledge and inspiration, offering a window into phenomena that stretch our understanding of the universe while captivating the imagination. In its safe, spiraling brilliance, beauty meets science, and the cosmos invites us to watch, learn, and marvel. Even though the Pinwheel Star has shed its reputation as a looming cosmic threat, it remains one of the most enigmatic objects in our galactic neighborhood, brimming with mysteries that continue to challenge astronomers. Its spiraling dust, intricate binary dynamics, and potential as a future supernova progenitor present questions that are far from fully answered. The star embodies the duality of certainty and uncertainty in science. We now know it is unlikely to harm Earth, yet its internal processes, future evolution, and broader implications for stellar physics remain profound puzzles. One of the enduring mysteries lies in the precise mechanics of its dust formation. While colliding winds clearly produce the visible spiral, the efficiency of dust condensation in such high-energy environments is still not entirely understood. The temperatures, densities, and chemical pathways that allow solid dust grains to survive in the face of powerful ultraviolet radiation and supersonic winds are subjects of ongoing research. Understanding these mechanisms is crucial, not just for the Pinwheel Star, but for broader questions about how massive stars enrich the interstellar medium with the elements essential for future generations of stars and planets. The binary system itself also conceals secrets. Although spectroscopy has revealed the orbital tilt and dynamics of the stars, there may be subtle variations in mass transfer, wind speeds, or orbital precession that are not yet fully mapped. These hidden complexities could influence the star's eventual supernova or the formation of any relativistic jets. The very presence of the OB companion raises questions about how binary interactions affect the timing and nature of core collapse, and whether similar systems elsewhere in the galaxy could produce gamma-ray bursts with different properties.
Another layer of mystery involves the star's ultimate fate and its place in the life cycle of the galaxy. Even though the supernova and potential gamma-ray burst are tens of thousands of years in the future, predicting the exact conditions under which these events occur is challenging. Stellar evolution models continue to refine our understanding, but each Wolf-Rayet system presents unique parameters, mass, rotation, composition, and binarity that can dramatically alter outcomes. The Pinwheel Star serves as a reminder that even stars we study extensively can harbor surprises, and that cosmic evolution is a process with both predictable patterns and wildcards. Additionally, there is the intriguing question of perspective. Why does the spiral appear so face-on, even with a tilted orbit? The answer likely involves complex interactions of winds, dust formation, and projection effects. But fully reconciling the visual appearance with the orbital geometry remains an active area of study. Resolving this puzzle could illuminate not just the Pinwheel Star, but the broader physics of colliding wind binaries and the behavior of dust under extreme conditions. Finally, the Pinwheel Star represents a broader lesson about our relationship with the cosmos. Once feared as a Death Star capable of ending life on Earth, it now stands as a beacon of discovery, a star whose secrets inspire both awe and inquiry. Its continued observation reminds us that the universe is not static. Stars evolve, binaries interact, and even the most apparently familiar objects can hold surprises that challenge our understanding of physics, chemistry, and cosmic evolution. Though the immediate threat is gone, the mysteries of the Pinwheel Star remain. Its spiraling dust, dynamic binary motion, and eventual supernova will continue to fascinate scientists and skywatchers alike, a cosmic puzzle that invites decades, if not centuries, of observation and exploration. It is a star that blends danger, beauty, and enigma, a reminder that the universe is both knowable and infinite in its complexity. In watching the Pinwheel Star, we are not merely spectators of light and dust. We are witnesses to the unfolding story of stellar life, a story that continues to challenge, inspire, and enthrall.
This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.